So as I'm recording, there's this nice thunderstorm that's passing by over Mumbai. The monsoon is pretty much over, but we still have some activities going on. So there is some nice thunder outside, which I love. But if you hear it through the recording, don't panic, okay? Let's look at this again. I mentioned something already, that the asymmetry of the warming period and the cooling period, both corresponding to a positive ice albedo feedback, and the glaciation slows down because air gets colder, drier, snowfall rates fall, etc. The ice albedo feedback can go very fast in the melting phase, and we have to be careful now because we are in the melting phase. We are increasing greenhouse gases, we are warming the temperatures, glaciers are beginning to melt away in Greenland, Antarctica, in the Alps, in the Himalayas, and so on. So this can go very fast, which is called abrupt climate change. And there are some evidences from 12,000 years ago that the changes can happen on just a few decades. So that's really fast. Why do we worry? Because the amount of sea level that's locked into these glaciers is massive. It's a total of over 300 feet, more than 100 meters. So that's not funny, right? If that happens, many places like Florida and Manhattan, many island states, many low-lying coastal areas are going to be in serious trouble. But even before you reach the full change, cyclones are going to sweep in more and more water if the sea level keeps rising, which is already happening. Okay, so let's focus on this last part where we said since the Industrial Revolution, we have increased CO2 and methane beyond anything that's seen in this record, but also other proxy records that are taken back to several million years old, almost 20 million years long, and which means we have gone beyond what is seen in the last couple of tens of millions of years. So we are really in a la-la land when it comes to greenhouse gases in the atmosphere. Okay, but you can see that the temperature, which was quite in phase with the atmosphere, with the atmospheric carbon dioxide and methane, it led by a few thousand years, as I said, up to 30,000 years, because orbital forcing, radiation change, first begins to change the temperature. Then the ice albedo feedback kicks in, and then the CO2 and methane respond based on whether the ocean and the land are getting covered by glaciers or they are being exposed by the glacier, and so on. And that range is about 100 ppm from ice age to deglacial age and back. And there are many theories to explain why this happens. For example, dust in the atmosphere increases when it's cold and dry during a glacial period or an ice age, and dust tends to contain iron in it. If you dump iron on the ocean, remember your biology now, iron can be a limiting nutrient. So in some places like the Eastern Pacific, where there is upwelling and production, and the Southern Ocean, if you dump iron, you're going to increase photosynthesis, which means you're going to sequester more carbon into the ocean. And there are other, like sea level changes, so phosphorus content increases at the coastal interface and the shelf, and so on. Coral hypothesis, because corals change as you change the sea level, and so on. So, coming back to this fact that temperature has not risen as fast as in the past when the greenhouse gases have increased. The first thing to notice is that in the past, orbital changes were changing the temperature first, and then CO2 and methane were following. But what we are doing now is we are increasing greenhouse gases first. So we have increased CO2 by fossil fuel emission, methane by coal burning as well, and rice fields, cattle, wetlands, dams, and so on. So the system is in a different mode now. We are increasing CO2, CO2 has to increase the temperature, and then the ice albedo feedbacks kick in. So temperature has begun to increase, has increased by a degree centigrade since the Industrial Revolution. Ice albedo feedback has started. Glaciers are melting on Greenland and Antarctica, and sea ice over the Arctic is melting. Snow is melting on land as well. But since the process is different, the change in the temperature is not caught up yet. This means two things. One, if you go back and remember that the residence time of greenhouse gases are long, other than water and methane, which are 10 days and 10 years respectively, CO2 can hang around for a couple of centuries. CFCs, HFCs, and other things can hang around for multiple centuries, N2O for 300 years, and so on. So even if we somehow magically stopped emitting all greenhouse gases today, the long residence time greenhouse gases are going to hang around in the atmosphere. Slowly they're going to get into the ocean, taken up by photosynthetic plants and ocean and so on, but that's going to take time. So that is called committed warming, which means by emitting the CO2 and other greenhouse gases since the Industrial Revolution, we have locked ourselves into a warming that is guaranteed, because even if we stop our emissions completely, warming will continue for a while. That is why it's called committed warming. So this warming will continue even if we stop the concentrations here and even begin to take it down to some extent. Okay, so you can see here again, just to tell ourselves that the atmospheric concentration we keep talking about is in parts per million. We are over 415 now, 2020, end of 2019. 2020 data will come in a little bit later. But this CO2 has been accumulating in the atmosphere. This matters because when we go back and try to assign responsibilities for who is causing the global warming since Industrial Revolution, then it turns out to be a different game than if we look at the more recent period, let's say since 1990. Okay, so the CO2 emissions in billions of tons per year has also been increasing since about the First World War. Second World War really ended and then really accelerated the economic growth everywhere in the US, Germany, Japan, and so on. And the mode of operation also changed. Things began to be built to be more dispensable because people like Victor Lebo, who was a retail salesperson, wrote a little paper saying if we want to constantly grow the economy, we must build things that don't last very long so people buy new things. But now it's even worse, because even if your iPhone is doing just fine, you're going to buy a new iPhone. You means many people are going to buy a new iPhone by getting rid of the old iPhone or turning it in, right? So consumption has gone up, production has gone up, energy production is still from fossil fuel based high carbon footprint kind of sources. Economies are growing. India and China want to grow. They should be allowed to grow, of course, but as GDP grows, energy usage goes up, emissions go up. So per year we are emitting somewhere between 35 to 40 gigatons of carbon. You can convert it into carbon equivalent by including other greenhouse gases, then this will jump to about 50 and so on. Okay, so here is a cartoonish way to say it. Let's say in 2000 we decided to either somehow magically stop the emissions after 2010, in which case the concentrations in the atmosphere will begin to drop. But look carefully at this axis here, the abscissa. It's going out to 2300. So we are talking a couple of centuries into the future. So the concentration drops very slowly because CO2 is inertial, is an inertial gas. It doesn't react very much, and it's taken down slowly by trees and oceans and wetlands and other things. Whereas if you keep constant CO2 concentrations after 2010, we are going to maintain some sort of a concentration in the atmosphere. So the emissions per year will correspond to these kind of curves, and the temperature, which is what we are interested in, you can see that if we cut down to zero emission, the warming continues into 2300, and if you maintain constant CO2 concentration, CO2 begins to accumulate in the atmosphere because it has long residence time and is not taken down so quickly. So you can see that temperature continues to rise. Okay, how much this rises depends on where the CO2 will be taken up, whether the oceans will get saturated, and how sensitive the climate is, which means climate sensitivity is a very important term. Maybe I'll come back to it later, but basically we do a simple experiment where we say we double the CO2 concentration and keep it there and see how much the equilibrium change in temperature would be as a global mean. Will it be 2 degrees? Will it be 4 degrees? And this can be partly inferred from past climate changes. For example, during the Little Ice Age, we know how much radiation change was. We know how much CO2 change was, and we can try to infer climate sensitivity. But that's called a transient climate because CO2 was not equilibrated, it kept changing. Complications, but nonetheless climate sensitivity is a buzzword that you should remember. So carbon climate response, delta T over emission over time, is complicated by carbon sensitivity of the climate, CO2 emissions, and accumulation in the atmosphere. Remember, some is going into the forest, ocean is taking up about 25%. So we tend to measure CO2 concentrations in the atmosphere because it's easy to measure. Well mixed gas, remember, you can measure it at 1 or 2 places and know the whole concentration. But that leads to temperature change. So there are climate carbon feedbacks in the system which determine the net response of the system. So the key concept here is committed warming. Doesn't mean that we shouldn't worry about reducing carbon emission. Reducing carbon emission does reduce future warming. That's different than saying that the carbon we have emitted already does provide us a committed warming. Okay? Because if we do things like carbon capture and sequestration, then we can begin to take down carbon dioxide out of the air and slow down the warming rates much further as well.